It's a pleasure to welcome John Baez to Topos Institute.
Okay, well, great. It's great to be able to give this talk here because Brendan Fong helped start this theory of decorated cospans, and he's here in the audience, and he's in the Topos Institute is one of the things he's running right now. And so in some sense, this is all part of a story that somehow started in Singapore when he came to be a summer intern when I was working in Singapore, and I liked him so much that he liked me so much that we decided to keep working together, and then somehow he wound up here. So, so this is a picture from a paper that he wrote that started this business. So it was around 2012, after he'd already been to Singapore, that I asked Brendan as a thesis project to create and to define and study a category that has open electrical circuits as morphisms. And this is a picture from there. So you have a circuit here with some resistors of different resistances measured in ohms, that's that omega, and some inputs and outputs, which are wires that are sort of dangling out that you would feed electrical current into. And so he took forever to do this simple project, but then when he started when I actually started coughing up results, he'd done some much more general and important thing, which is he invented the theory of decorated cospans, which is a general theory for describing things like electrical circuits or graphs or Petri nets or other things with inputs and outputs and how you stick them together. And so he published a paper called Decorated Cospans in 2015 describing that theory. And then it took us a while to finish our paper jointly on electrical circuits, where we applied that to the original problem of electrical circuits by 2018. And decorated cospans have been used for many other purposes since then. I had a bunch of grad students, and there for a while everyone was working on a different decorated cospan category for Markov processes or Petri nets or other things like that. But they're quite subtle. They turn out to be quite subtle, and a lot of those early papers actually had mistakes in them, and I feel that they were only fully understood in 2021, this year, and I'm not even sure, of course, that that's true. So 2021 or later, I should probably say more conservatively. So I'm going to show you the problems of decorated cospans and then how they are solved. And I want to have an example in mind, so I'm going to use the simplest example, which is not the most exciting example, but it's the example where you have open graphs as morphisms. So an open graph is just a graph, as shown here in the middle, together with functions from two sets, let's say finite sets, into the vertices or nodes of that graph, which you use to describe the inputs and outputs of that graph. So this graph here, this open graph here, should be a morphism from the set A to the set B. And the idea is that we'd like a category where these are morphisms, and you can compose them by sticking them together at the inputs or outputs. So if I had another open graph over here, whose inputs were the set B, I should be able to stick it together and get a new graph going all the way from A over to this set over here, which could be called C. And so it's a really simple idea, right? You're just sticking blobs of stuff together, and they should compose associatively, and so you should get a category. So it's sort of remarkable how long it's taken to sort this out. But it's a very important concept, I think, so it's worthwhile, because it's a concept of you've got some kind of stuff and you're sticking it together, and you're sticking it together along the boundary, and the boundary may be a slightly different type of stuff than the middle, and often a simpler type of stuff. So here the boundary is just a set of dots, but the stuff in the middle has edges too. So that's what the level of generality is that we want to be able to handle. So in this example, an open graph is a cospan of finite sets. So you have these two sets, A and B, both getting mapped into this set N, which is the set of going to be the set of nodes of the graph. But you start out with just a cospan of finite sets, and then you equip the apex of that cospan, the set n, the finite set n, with some extra data, which makes it into a graph. So you equip it with an extra set E of edges and source and target functions to n. So that's the idea. I'm going to work with finite sets here, and it actually makes a little bit of a difference. So Brendan's idea was to abstract from this and think of this as a cospan where the apex has been decorated in some manner. The apex has been decorated with this graph. So in his approach, it was decorated by choosing an element in some set, which we'll call f of n, which is the set of all graphs with n as their set of nodes. So you just pick out an element of that set and attach that, so to speak, to the apex, and that's your decorated cospan. And then, starting from that type of example in mind, he proved this theorem. And I should say, while there are certain problems with applying this theorem, there's nothing wrong about the theorem. The theorem is perfectly valid. And so here it is. So you start with a category A that has finite colimits, and you start out with this functor from A to set, which you require be symmetric lax monoidal, where A has coproducts providing its monoidal structure, and set has products providing its monoidal structure. And then, given this, you get a decorated cospan category. So you get a symmetric monoidal category, in fact, of, say, F decorated cospans. And so the objects are just the objects of A, whereas the morphisms are cospans in A, or actually isomorphism classes of cospans in A, but crucially decorated, meaning that you pick out an element D in the set F of n. That would be like picking out our graph in the previous example. And so we call D the decoration, and then we have to say what the equivalence relation is on these decorated cospans, so that when you compose them, it's actually associative. A composition and a category, it's got to be associative, and that sort of forces that you impose an equivalence relation here. And so we say that two decorated cospans are isomorphic if there's an isomorphic. So here they are. Here's one of them on top here, and here's another one here. So they have these apexes m and m prime, and so we say the decorated cospans are isomorphic if there's an isomorphism from m to m prime, making both of these triangles commute, but also mapping the decoration of the one cospan over to the decoration of the other cospan. I mean, that's pretty reasonable definition. There's not really much you can tweak about this without completely changing the idea. This is sort of the obvious good thing to do. And so to understand the theorem, the main thing you've got to understand is just how do you compose these morphisms. So if I've got two different decorated cospans where the target of one, B, is equal to the source of the other, then we compose them in the following way. So here they are as cospans, and we compose them the usual way we compose cospans, which is by taking a push out in the middle here. And so here I've actually drawn the coproduct of m and n, and then that maps down to the push out over B. So there's this canonical map from the coproduct to the push out, which I'll call psi. And so as a cospan, the composite is just this big fat cospan here. That's the usual way you compose cospans. The only interesting thing is how you provide this cospan with a decoration. And so you do the sort of obvious thing. You've got a decoration D on your first cospan and a decoration E on your second one. So you've got an element of the set f of m times f of n. But then here's where it comes in that our functor f was lax monoidal. Because it's lax monoidal, it means there's a map from f of m times f of n to f of m plus f of n. So we push the decoration, we push this pair of decorations forward into becoming a decoration on m plus n. But then because f is a functor, you can also apply f of psi to that and get an element of f of m push out n. So you get your decoration on the push out. So the idea is, in the case of graphs, if I've got a way to put a graph structure on a set M, that is, get a graph whose set of vertices is M, and another graph structure on the set N, so another graph whose vertices is M, then of course I get a graph whose set of vertices is the disjoint union of M and N. That's just setting them side by side. So that's what's providing the lax monoidal structure, supposedly. And then when we stick the sets together, we can stick the graphs together. That's the idea. This only needed F being lax monoidal, but to make the category that we're after to be symmetric monoidal, you turn out needing F to be symmetric lax monoidal, as you might expect. Okay, but there are problems with this, some of which Brendan and I very rapidly realized, and others of which were only realized much later. And so I'm going to apply them, I'll describe them in historical order, which unfortunately is also the order of increasing seriousness. So it would be nice if it were the other way around, like first we solve the hard problems and then like, oh, there's a few little extra things, but no, it's sort of more nerve-wracking as history goes on. Well, I guess that's fun for a TV show or something like that, or the last minute, it's like a cliffhanger. But so the first problem that I noticed right away, because I'm a little bit of a stickler about these things, is that the so-called set of graphs whose set of nodes is n, it's not really a set, it's a proper class. There are just too many of the darn things. Even if you restrict E to be a finite set, as I've done here, there's not a set of all finite sets, it's a proper class. So this F here is not really a functor from fin set to set. It's something like a functor from fin set to classes. Well, there are luckily various well-known workarounds for this problem. For the purposes of this talk, I'll pick one, which is we replace the category of finite sets by an equivalent category that's actually small. In other words, one that just has a set of objects. And you can do that because you can take a skeleton of any category, and that'll be an equivalent category. And a good skeleton of fin set is the category where the only finite sets you care about are 0, 1, 2, 3, 4, 5. So you have one set of each natural number of objects, and that's all the sets you need, because every other set is isomorphic to one of those. So we'll do that, and we'll just call that new improved version of fin set, and so that nobody who was not paying attention will even notice that you've done that, and they'll never be the wiser, and they'll be perfectly happy, and we've solved that problem. There would be other ways to solve the problem, but this is not really that big a deal. Okay, that was just number one. Number two is something that I realized after we had begun applying this to some examples, so some papers had already come out, and then I thought, oh no, there's this other problem, which is that, remember, when we constructed this category, we imposed an equivalence relation that said when two decorated cospans were going to count as isomorphic, and those would then be the same morphism. But when you examine what that really is, what that really amounts to in this example, you see that it's something a little funny is going on. Here are two different decorated cospans, both from the same set S to the same set T. And if you follow the definition that I gave you in that slide that presented the theorem, these decorated cospans are not isomorphic. So who can tell what's different about these two decorated cospans? What's different about them? Yes?
E5 and E6.
One of them, the edge is called E5, and the other, it's called E6. And believe it or not, that makes these decorated cospans not isomorphic. Now, of course, they should be isomorphic. It's not supposed to be that if you change the name of something, it makes it non-isomorphic. But you actually have to use the definition that I gave on that theorem slide to see if they're isomorphic or not. And so let's do that, and we'll see that they're not isomorphic. So, okay, so remember, a graph whose set of nodes was n was an element of this set f of n. And the way we could get another isomorphic open graph involved picking a function from n to n prime, which is actually, we wanted to pick it to be an isomorphism. And then given such a function, we get a new graph whose set of nodes is n prime. So how does that actually work? Well, the way it works is sort of the obvious way, which is that if you had a graph whose set of nodes was n, it has these two functions, s and t, and then if you post-compose them with h, you get functions to n prime. So you get a new graph whose set of nodes is n prime. But you'll notice that the set of edges of this new graph is exactly equal to the set of edges of the original graph. So in this concept of isomorphic decorated cospans, you can use the isomorphism to change the names of the nodes of your graph, but it's unable to change the names of the edges of your graph. So if the two open graphs have different names for their edges, they're not isomorphic. And so when we form this category of decorated cospans, there will be lots of morphisms in it, that is, lots of open graphs that look isomorphic, like in the picture, but aren't isomorphic. So they're different morphisms. So two solutions. One, just get used to it. That's actually a general solution to all problems. Learn to live with the fact that there are like lots of open graphs that look isomorphic, but technically aren't. Now, that's probably not a great solution. The reason why we were able to have this problem and not instantly got hit over the head with it is that we were very often using decorated cospans as semantics, and we were mapping out from them to other categories to see what they did. If you have lots of duplicate copies of things that should be equal but aren't, that doesn't cause a problem when you map out, because you just map those duplicate things to the same thing. But if you ever dared to map into a decorated cospan category, which is probably bound to happen sooner or later, then you're running into trouble because you don't know which of the duplicate copies to pick. So you could, I mean, we wrote a number of papers that were correct, but just suffering from this problem. But you know, they didn't make the theorems false. There's another solution, which I adopted once I realized there was this problem and before I had thought of any better solution, which is in this example, don't let f of n be the set of graphs with n as its set of nodes. Let f of n be a set of equivalence classes of graphs with n as its set of nodes. So the idea here would be, don't use this f of n here, but say, take a quotient set of this set f of n, where you say that if I had some other graph with n as its nodes that looked just like this one, but with like some new set of edges e prime that was isomorphic to e, I'll count those as the same. So there's an equivalence relation you can slap on f of n, mod out by that, and then you get rid of these duplicate copies. There's one big problem with that, which is, I mean, well, it works. In other words, you do get a decorated cospan category. It does have just as many morphisms in it as you want, but there's still something a little annoying about it, which really doesn't show up at the level of the category of decorated cospans. It shows up later, which is that you can't point to a specific edge in an equivalence class of graphs. So it's just like if I have an isomorphism class of sets, as opposed to a set, I can't talk about an element because there's no such thing as an element of an isomorphism class of sets. So the way I think of it is like a slippery pig. If you have like a pig that's so slippery and twisting around, covered with oil, you can't like actually grab onto any leg of the pig. It's like any leg could be just like any other leg. And so it's like, you could say like, hey, I've got a pig. But then but someone says like, well, show me its right leg. You say, sorry, I can't. It's like wiggling around too much for me to show. Yeah, it's leg. So it's not a very useful thing to have when you try to actually grab a specific edge of one of these isomorphism classes. Then the third problem is actually much worse than the other problems. It turned out that Christina Vasilikopoulou and Joe Moeller wrote a paper, and they submitted it for publication, and they mentioned decorated cospans as like an example of their construction, which is a paper on the monoidal Grothendieck construction. And the referee of that paper said, hey, by the way, did you know that that paper is wrong? That has this mistake in it. That is about this graph thing. It had a mistake in it. That this functor, f, the referee pointed out, was not lax symmetric monoidal, really. In fact, there are problems both with it being lax monoidal and problems with it being lax symmetric monoidal. Turns out the monoidal part, you can dodge the bullet, but just barely. But the symmetric one, you're really dead. So let me just cut the story short a little bit and just tell you the lax symmetric monoidal problem. So a lax symmetric monoidal functor has got to make a certain diagram commute. So here is our map, which I call the laxator, which in our example, remember, it takes a graph with nodes n and a graph with nodes n prime, and sets them side by side and gives you a graph with nodes n plus n prime. And then there's this symmetry or braiding in the category of in finset plus and also of set times, which is what these two arrows are here, and that just switches two things around. So here what we're doing is we're just just switching these two things around and then combining them into a single graph. And here we're combining into a single graph and then switching them around. And this graph does not commute. This diagram does not commute. And the reason why, again, comes from these damn edge labels, the fact that the edges actually matter. Well, it's the fact that the set of edges actually matters. So if you look at it carefully, like say I had some graph over here whose set of edges was E, and another graph whose set of edges was E prime. If I combine them, I get a graph whose set of edges is E plus E prime. And then if I do this, it stays E plus E prime, because you do not do anything to the edges. Whereas if I go around here, now I've got a set of edges E prime and a set of edges E, and then when I combine them, I get a graph whose set of edges is E prime plus E. Well, of course, E plus E prime isomorphic to E prime, to whatever the other one. the plus is commutative up to isomorphism, but it's not commutative on the nose. Those sets are not equal, and that's enough to make the diagram not commute. So again, we have done something terrible in the first place, and which is punishing us as we go further into this. A similar problem happens with the monoidalness as opposed to the symmetry. So plus is also not strictly associative. It's associative up to isomorphism. Well, it turns out there's this thing called Maclane's strictification theorem, which says you could replace your category by one where the plus is strictly associative, but you can't make it be both strictly associative and commutative. So the commutativity, like at that point, you ran out of tricks and you're dead. Okay, so this is really a problem. So in other words, we cannot use this whole setup to get a symmetric monoidal category of open graphs, unless we use this trick of working with equivalence classes. That would work. So that you could do that. Okay. Well, yeah, okay, so here I said it. So one way out is you work with this equivalence classes of open graphs. But a better solution is to go back to the drawing board and figure out what the heck is going on and really straighten it out, right? Because we should not be having to squirm around so much when we're doing such simple category theory. So it turns out there are two good ways to solve all these problems. So one is the theory of structured cospans, and the other is what I'll call the new improved theory of decorated cospans. So it turns out, roughly, just to give you an overview, they're going to be equivalent in cases when they both apply, but structured cospans are easier, so when they work, you should probably use those. But decorated cospans cover some examples that structured cospans don't cover. So everything is explained in these papers that I wrote with Kenny Corser and Christina Vasilikopoulou. So first, Kenny and I came up with structured cospans, and then the equivalence between them and decorated cospans is explained in this last paper, but here we had to introduce the new improved decorated cospans to get it all to work. So here's how it goes. So for starters, both these approaches are going to give symmetric monoidal double categories. So in other words, instead of just objects and morphisms, we're going to have two morphisms going between morphisms. And here's an example of a two morphism from one open graph to another. So it's a map from this set to this set, and a map from this set to this set, and a map from this graph to this graph that makes everything commute. And so in particular, you see that like we're able to collapse two of these inputs down to one. So those are both getting mapped to there. We're able to map two edges down to one here. We are able to relabel edges. Woohoo! We're able to map an edge called E3 to an edge called F2. That's not so surprising anymore. I mean, when you have maps, of course, they should be able to map things to things of different names. And you can also include your graph into a larger graph, so you can stick in some extra edges. So all of that is stuff that you would like to do. But you need this extra level of category theory, double category, to do all this stuff. Now, if you don't like double categories, well, you should like double categories, but you might not like symmetric monoidal double categories. That's starting to get a little bit complicated. So the good news for those types of people is that you can water this down, this theory down as ad libitum. If you like bicategories, you can turn these double categories into bicategories. Although if you ever studied symmetric monoidal bicategories, you'll realize that you should use symmetric monoidal double categories because symmetric monoidal bicategories are really complicated. But if you don't like any of that stuff, you can water them down further and get symmetric monoidal categories. And so I'm expecting that like most people who ever use this stuff are just going to use that. But actually to get those categories, the best way to have time is to start with a double category and then deliberately do a process that turns it into a category. So I'll just tell you about the double categories. Okay, so the reason why there are these two approaches is that there are two different ways, at least, to equip an object of a category with some extra data. So remember, the key thing was that we had this cospan of finite sets, and the set on top, we wanted to equip it with some extra stuff to make it be a graph. And so what's going on when you're doing that sort of equipping? Well, there's two ways that are both pretty common. So one is you find a functor from some other category to A, which you would think of as a forgetful functor, that is technically a right adjoint. And one way to give an object A of the category A extra structure is by choosing an object X and X such that R of X is equal to A. So like if I've got a set and I want to make it into a group, I say, hey, there's this right adjoint functor from groups to sets, the forgetful functor, and I just pick a group whose underlying set is my set. So that's a very common way to think about equipping things with extra structure. But there's this other method, which is more true to Brendan's idea of decorating. And it's a little bit more complicated, actually. So remember, Brendan's idea was to think about a functor from A to set, where you get a set of possible decorations that you can slap on an object. But see, part of the problem, reason why it didn't work is because there's not really a set of graphs with a given set of nodes. What there really is a category of graphs with an extra set of nodes. That's the better way to do it. So what we really should have is a functor from A to cat, but it doesn't need to preserve composition on the nodes. It's enough to preserve it up to isomorphism in a coherent way. So it's what Grothendieck, I guess, called a pseudo functor from A to cat. And then to decorate A, we pick an object D in f of A. I'll give examples of both of these. So the first one is more convenient because it just uses a pretty low-level categorical concept of a right adjoint functor. Whereas the second one is a little bit more sophisticated. You're really getting into some two-category theory here because this is a pseudo-functor from A to the two-category cat, but it is more general. And so one thing we'd like to do is to relate the two approaches. And so to relate the two approaches, the key is this thing called the Grothendieck construction, which I'll describe in more detail, a little bit more detail. But the point is that whenever you have a pseudo-functor from A to cat, you get this new category called the integral of f, or the Grothendieck construction of f, which comes with a functor to A. And so the idea is that if I have a way to pick a category of decorations for any object of A, I can cook up this new category where the objects are guys in A with a decoration. And then there'll be a forgetful functor from them to A where you forget the decoration. Now the interesting thing is that functor is not always going to be a right adjoint. But it will be a right adjoint under some conditions. So our theorem needs to have some conditions. I remember at one point when I was starting to think about this, I asked André Joyal, when is this functor that they think about in the Grothendieck construction a right adjoint? And I thought like he'd instantly know like 7 conditions under which it was a right adjoint because it seemed like such a super obvious question because these are really two pretty standard ways of thinking about equipping something with extra structure and forgetting the structure. And he said, I never thought about that. So it turns out that not many people have thought about that. And so Christina Vasilikopoulou was our expert on figuring out how to solve that problem, to find these conditions and make that work out. So let's do the easy one. So if you've got a right adjoint, then a structured cospan is just you can think of it as a diagram in the category A, where this apex here is the underlying object in A of some object in X. So you should think of A as a category of objects with less structure, X is the category of objects with more structure, and R is the forgetful functor. So for example, A could be finite sets, and X could be graphs, and you're forgetting the edges. But it turns out to be technically nice to use the adjunction to reinterpret that diagram, reinterpret the legs of that span as morphisms from L of A to X. That's what adjunctions are good for. So it's sort of nice to focus on, technically nice to focus on the left adjoint that our right adjoint has and think of a structured cospan this way. And one reason why this is technically a little bit nicer is that now everything in here is just an object in X, and composition of structured cospans is just doing push out in X, and no extra conditions are required. Whereas before, you could be trying to do, over here, you could be trying to do push outs in the category A, but you wouldn't necessarily know that your new apex was of the form R of X. So you'd have to be worrying about that all the time. So this is the slick way to do it. And so then we get this theorem that says that it works. So if A and X have finite colimits, so that lets us do our push-outs and also let us do our coproducts that we do for some kind of disjoint union type instructions, like the symmetric monoidal structure. And if L preserves finite colimits, which it will do if it's a left adjoint, then you get this symmetric monoidal double category of structured cospans. So the objects are the objects of A. The vertical one morphisms are really just morphisms in A, but you draw them like this with drawing an L in front of them. And then the horizontal one cells, those are our structured cospans. And then we can talk about a two-morphism from one structured cospan to another, which is just a commutative pair of commutative squares like this. So this lets us map the objects in A to themselves and the objects in X to itself. So that's basically it. So the way vertical composition is completely boring and straightforward. You're just composing some morphisms. Horizontal composition is a little more interesting, a little bit. So if you've got two of these, two morphisms, you compose them by doing push-outs. So we're doing a push-out of these two cospans and then doing a push-out of these two cospans, and we get this. But it's all pretty much what you'd think. Proving that this thing is a symmetric monoidal double category takes some work. So Kenny and I first just tried proving it by going through all the axioms of a symmetric monoidal double category, and we did it that way, and we were very tired at the end of that. And then I realized that, like, come on, category theory isn't supposed to be like building a brick wall by hauling bricks one at a time and stacking them up. There's supposed to be something a little more intelligent about this whole activity. And so then I came up with a different proof that was nicer. And then quite a bit later, Mike Schulman said, hey, did you ever notice that this is all like just a corollary of a theorem that I proved? And I said, wow, okay, great. So in the paper on structured versus decorated cospans that we wrote with Christina later, we used Mike Schulman's approach. And we also used his approach for everything. Moral is, if you're going to work on double categories, talk to Mike Schulman about it before you write a paper. It's ridiculous. So, yeah. And, there's the symmetric monoidal structure. So that's really using binary coproducts, and also the fact that L preserves those, because if I have one of these and one of these, you want to put pluses everywhere to build a new one, but you see the object here really should be L of A1 plus A1 prime, whereas if I took coproducts in X, I'd get L of A1 plus L of A1 prime. But those will be isomorphic to each other in a canonical way if L preserves coproducts. So then we don't have to worry about whether the plus sign is inside the L or out. So we're using the hypotheses, in other words, of the theorem to make it all work. We need all those hypotheses. Okay, so that's method one, and it works. So that here's how it works. There's a category graph where the objects are graphs, and there's a forgetful functor to finite sets that takes the graph to its set of nodes, and it has a left adjoint that takes any finite set to the graph having those nodes and no edges. And so everything is ready to go. L being a left adjoint preserves finite colimits. These categories have finite colimits. So you get your symmetric monoidal double category of open graphs. And then if you don't like double categories, you can water it down and get a category, symmetric monoidal category. But then there's this other approach, the new improved decorated cospan approach. And I want to talk about that because that's sort of the new stuff in this talk. And so the key difference between this and Brendan's old approach is that we use a category of decorations instead of just a set. So if we have a lax monoidal pseudofunctor from A to cat, we can talk about a decorated cospan where it's just a cospan in A, but then there's an object D in the category f of m as our decoration. You can think of sets as a special case of categories, just the discrete categories. So this includes the old decorated cospans. It's just a more general. And sometimes the old decorated cospans would not have been a problem. It's just in the case of open graphs and others that it happened to be a problem. So this just sort of adds an extra layer of flexibility on the original construction. And so with Christina, Kenny and I proved the theorem that says how these decorated cospans work. So if A is a category with finite colimits and F is a symmetric lax monoidal pseudofunctor, then you get your symmetric monoidal double category of decorated cospans. So it sort of should look suspiciously similar to the structured ones. It is similar, but not quite the same. So the objects are those of A. The vertical one morphisms are those of A, are the morphisms of A. The horizontal one cells now are going to be decorated cospans. So M will be equipped with an object in f of M. Notice they're not any kind of isomorphism classes of decorated cospans. They're decorated cospans, okay? So we're not, no slippery pig problem showing up here. And then the two morphisms are just sort of the obvious thing, meaning a commutative diagram in the category A But now, instead of just saying that H sends D to D prime, we let ourselves have a morphism tau from f of H of D to D prime. So that's going to be allowing us to relabel edges in our example of graphs, because you could have an arbitrary morphism from one graph to another there. Take my word for it. The fact that there's not an equal sign down at the bottom here is saving the day this time. So then there's the question of when are these decorated cospans also structured cospans? Actually, we haven't completely nailed down all the issues about that, but we have this nice theorem. It's a little scary, but nice, saying when some decorated cospan double category is a symmetric monoidal one. So we start with the assumptions saying that we've got the ingredients for a decorated cospan category. And then there's this extra hypothesis, which is the thing that's going to make it all work, which is that the functor, well, it turns out that from a functor of this type, you can get a functor or pseudofunctor from A to Simon cat, the two category of symmetric monoidal categories. That's a fact that we need. And if that factors through Rex, so Rex is the king of all categories. Rex, or it's a two category actually, it's the category of all categories with finite colimits. If it factors through that, then you're in luck. Then the decorated cospan double category and the structured one are equivalent, are actually isomorphic, in fact. And they're isomorphic as symmetric monoidal double categories. But to define the structured cospan category, we need to know what I've been calling our X. In other words, you need to have the category of the more structured objects. Well, we just do the Grothendieck construction to F, and that'll be it. And so this extra fancy hypotheses here are what's required for this functor that I mentioned before from the Grothendieck construction down to A to actually have a left adjoint. So I said, like, it doesn't always, this thing doesn't always have an adjoint, but it will when this stuff is true. Well, as you can see, things are boiling up to a fairly high level of category theory at this point. And in particular, I sort of said, oh yeah, a functor from A, a symmetric monoidal pseudofunctor from A to cat corresponds to a functor from A to Simon cat, but I didn't say like what that was, so it's getting a little confusing, I admit. Well, let me at least answer that. So, a combination of paper by Mike Schulman and this paper by Joe Moeller and Christina, which is the one where the referee noticed these problems, showed there's a nice correspondence between three things. So say you have a category with finite coproducts, A plus. Then these three things correspond to each other. One is the thing that we're talking about with decorated cospans, namely symmetric lax monoidal pseudofunctors from A to cat. Turns out that when you have such a thing, right, each object of A here gets sent to a category. But it turns out that you can use all these pluses and timeses to make that into a symmetric monoidal category. It gets to be a symmetric monoidal category. And so it turns out that they correspond to pseudofunctors from A to Simon cat. You can go back. So that was proved by Mike Schulman, the equivalence between these two things. And then what Joe Moeller and Christina Vasilikopoulou showed is they also correspond to something else, which is in terms of this Grothendieck construction. Whoops. Yeah, okay. So, namely, you can, given a pseudofunctor from A to cat, you can build this category called the Grothendieck construction, and then it turns out that under these hypotheses, that thing gets to be symmetric monoidal itself, and the forgetful functor from that thing back to A is a symmetric monoidal functor, And it's of this kind that you get in the Grothendieck construction called an op vibration. So whenever you have the Grothendieck construction, you get something called a nice kind of functor called an op vibration from the integral of f back to a. But in this case, it's symmetric monoidal. And so Joe and Christina showed that these guys are equivalent to these guys. So the Grothendieck construction, probably a bunch of you know it, but probably a lot of people don't know it, is just this, that you start with this pseudo-functor from a to cat, and you build this new category where an object is going to be a pair consisting of an object in A together with sort of what I've been calling a decoration, namely an object in f of A. And then a morphism is going to be a morphism in A together with a map sending one decoration to the other in the following sense. So notice this thing should remind you a little bit of how I defined the decorated cospan double category. I was using this thing. So in the case of our graph examples, like f could send any set to the category of graphs with that set as nodes, then integral of f would be a set together with a graph having that set as its nodes, and this would be a map of the sets together with a map of the graphs, an arbitrary map of graphs. So it all works out. In particular, you get maps of graphs that can relabel the edges of the graph, so you don't run into that nasty problem that has been plaguing us. So the way I've been talking about the category of graphs for a given finite set, what is it? Well, there's a pseudo-functor from fin set to cat, sends each finite set to the category where the objects are just graphs having n as their set of nodes, but then there's a notion of morphism for those kind of graphs where since we fixed n, we don't do anything about n, but we have a map from edges of one graph to edges of the other that make the obvious diagrams commute. So that's not the category of all graphs, that's the category of graphs with a fixed set of nodes. But that's what lets us do the relabeling of edges. Yep.
So are you taking E to be any set?
Any finite set, yeah. Sorry to be so technical, but yeah, any finite set.
And
you
didn't take this, you don't want to take the skeleton for that, right?
Oh yeah, I actually do. Yeah, ha ha ha. Remember I said that whenever I said fin set from now on, I wanted it to be a category that's a small category that's equivalent to fin set. So whenever I'm talking about finite sets, I mean objects of that category. And the only reason why I need to be so sneaky like that is because I think you're alluding to the to the reason is that then we'll have a small category of graphs f of n. If we didn't do that sneaky stuff, I would have to write this cat like in all capital letters or something like that, which are like cost extra money. Well, it would mean like more size problems would hit us further down the road. So yeah, so we just we've replaced fin set by a small category that's equivalent to it, and we use that even here when we're talking about the when I say E is a finite set, I really mean it's an object in there. Yeah. You got to be a little careful with this business, but anyone who's programming computers will never know because they can't stick large categories into their computers yet. So then this pseudo-functor is lax symmetric monoidal given the sort of obvious map that takes a graph with nodes m and a graph with nodes n and gloms them together to get a graph with nodes n plus n. And then in this case, you can show that the Grothendieck construction actually gives you the category I'd been calling graph before, the category of all graphs. And then the Grothendieck construction gives you this functor from integral of f down to fin set, and that is just the forgetful functors from graphs to sets that pick out the set of nodes, and then it will have a left adjoint, and that will send each finite set to the graph with that set of nodes and no edges. So it gets back to where we were over in the structured cospan way of thinking about things. So it's all consistent. Yeah?
So what properties of f made that left adjoint exist?
There are probably different ways to say it, but I'm going to stick to my story, which is that this factors through Rex. So it's a sort of technical thing. Yeah, it's a somewhat technical thing. Meaning that the way in which the category of graphs with a given set of nodes, okay, the category of graphs with a given set of nodes is symmetric monoidal. That's the first thing I'm claiming here. What is the way it's symmetric monoidal? You just take the unions of the disjoint union of the edge sets. And that is actually coproduct in this category that I'm calling f of n. And so it's not just any old symmetric monoidal category. It's a symmetric monoidal category that is actually has finite colimits, and the symmetric monoidal structure is coming from coproduct. So that's the machinery behind the scenes of the proof. Yeah. And I should say that the proof that you get this equivalence, the proof of this theorem here is again a corollary of a result of Mike Schulman. So Mike Schulman not only gave a super general construction of double categories, which covers both of these as special cases, he also came up with a super general theory of when you get equivalent things that way, which covers this case. So it's just like, hand it over to Mike, let him do all the work. We had come up with a proof on our own before, but it was so ridiculously complicated that we actually didn't include all the calculations in our first version of our paper, whereas now we can just say, look at that other paper. We still have to do some work. And so, yeah. So the general theory here shows that these two approaches to the specific example of open graphs give you actually isomorphic symmetric monoidal double categories. But there are also examples of decorated cospans that you can't do using structured cospans, some of which we've actually used in our sort of applied work, like on chemistry. So it's good that decorated cospans are there. And that's it. So that's the story. Yeah, Evan?
So you mentioned that the theory of these improved decorated cospans is more general than structured cospans. Are there some interesting examples of things that are covered by decorated cospans but not structured ones?
Yeah, exactly. And you are working with them. So
That's good to know.
yeah. Yes, you didn't know it, but so one of the great examples that Evan has been working on is there's this I'll say category, although it's a double category. There's a category of open Petri nets with rate constants, and then there's this other, and that's a kind of semantics, and then there's this syntax where it's a category of you could call them open dynamical systems of a certain sort, which where you use some laws called mass action kinetics to translate your open Petri net with rates into a bunch of differential equations. And that second category can only be done with decorated cospans, not with structured cospans. The second category, the way it works, is that an object is a finite set. You can think of it as like a finite set of different kinds of people if you're applying this to epidemiology. Here's another finite set. You have a cospan of finite sets, but then on top, you decorate this finite set with the following thing. So this set is some set x. You look at the vector space R to the x, which you think of as like the set of possible population functions for different kinds of people. And then you put a vector field on R to the x, which you would use as the basis of writing down a first order differential equation that functions in R to the x can evolve with. So it turns out that kind of thing you can't do it with structured cospans because there's no right adjoint functor that forgets the vector space and the vector field and gets you back down to a set. And I guess it may be sort of easier to see why there's no left adjoint. And the reason why there's no left adjoint is that there's no God-given best way to pick a vector field on R to the x. You can pick 0 because that's like an obvious vector field to try, but that doesn't have the universal property. It doesn't map. You can't get maps that like map the 0 vector field to any other vector field. It just doesn't have the left universal property. So yeah. So that's the key. That's the only example I know right now that where I really see that. Although I bet there are tons.
That's a good example.
Yeah. Right.
But you don't need a full left adjoint, right? You only need it to preserve finite code.
That's true, but this doesn't even.
Yeah.
Okay, I should check, but I don't think it. I don't. Whew, boy. Okay, I'll have to think about that. That would be amazing if that weaseled out that way. That would be cool, but I somehow don't think it's going to do it. Yeah. Yeah, David. Sorry.
So I'm wondering how well this dualizes. If I don't think too hard, can I get decorated spans by just taking all the co-limit stuff and turning it into limit stuff in that big theorem? Decorated spans.
Yeah, I would have trouble quickly answering that because there's a lot of stuff that. Yeah, I don't know is the short answer. So I mean, you have to turn your co-limits to limits here. You have to turn your plus to times here. I think Joe. What?
Isn't that it? I mean,
Well, maybe your rex turns into your rex would turn into a lex.
That might
See,
be it.
the sneakiest part is that there's like a handedness built into this notion. So it might be that you just turn rex into lex, but it's yeah. I mean, but there's actually like stuff involved in showing this theorem, and so I'm not really couldn't like guarantee that it's all going to work. Yeah, it's worth trying.
Like a practical issue that like in the examples where you want to use structured spans like pullback, you can't actually use the actual categorical pullback doesn't give you the right thing. Like there are some like I can think
I don't know. I've never.
Example, but like in your paper on the classical mechanics was that part of the issue there?
Yeah, so we were trying to study open classical mechanics systems using some kind of structured spans, and we ran into trouble. But I don't think it's like a category theoretic problem that like limits were worse than co-limits or something. It just turned out to be that like in that example, the whole concept of decorating an open span turned out to be that we needed to make it true to the physics was different than just decorating the apex. We needed to decorate the apex and the feet with extra structure as well, which came as a big shock. And so that's like some new theory that we've only worked out in a couple of examples, so it's sort of mysterious so far. David, yeah.
if you're a functor from C to cat, from A to cat, sent every object of A to a category with an initial object. So like in graphs, you could say graphs with n nodes has an initial object named with empty set of edges. Do you know if that's sufficient to get?
Oh, sneaky. Christina, I do not know. Christina kept on complaining that this theorem was like had stronger hypotheses than were needed. And I was like so tired I didn't want to like worry about it.
Yes, fiberwise initial objects are equivalent to the left adjoint.
Okay, I thought.
Whoa, okay. Yeah, no, that's true. I do know that.
Yeah.
But
The other stuff is more stuff, but just the left adjoint is fiberwise initial.
I was thinking about like the whole shebang, but yeah, okay, for that. Yeah, that's right. Yeah, that's actually stated as like a lemma in our paper, and it goes to, we recited to, what's his name? Hermida, I think, has that. Yeah. Yep. Yeah, there's some fun interplay between the theory of fibrations and op fibrations and left and right adjoints, and it seemed like the people who were thinking about that were Hermida and also John Gray, and so the somewhat old papers turn out to hold a lot of clues.
So Brendan originally decorated cospans as a hypergraph category, right?
Right.
And that extra structure is really useful.
And that's what you're going to do your thesis on.
Oh.
Prove that it's a hypergraph, double symmetric monoidal category. Yeah.
So nobody's gotten around.
Nope, it's waiting for you. It's got your name on it. This is the way you punish people who ask questions like that. Especially if they're your grad student. Yeah, no one knows what a hypergraph bi-category or double category is
Shulman
yet.
basically does.
Oh, well, he does? Well, okay. Yeah, why didn't I think of that? Okay, you don't have to do it. You just ask Shulman and he'll just send the answer in an email. Yeah. He sketched out the proof of this theorem in an email that was just 2 paragraphs long, and then we to spend 6 months understanding it and then working through the details. But he was perfectly right. Yeah. Yeah.
So regarding the conditions in this theorem, which I admit I don't understand very well, in practice, would you try to check this condition regarding factoring in Rex, or would you just look at the functor R, the projection in functor R, and see if it has a left edge? Are these the sort of conditions that one can readily check, or is this?
I think that in practice, yeah, I mean, we haven't run around using this theorem a lot yet. So I think in practice, it's the first and least painful step is what you suggested, which is just to figure out this thing, the category of decorated objects, look at its forgetful functor, which is some obvious functor. I mean, that exists, and then just guess.
Try to guess the adjoint.
Guess the left adjoint. Then yeah. And so, if there is a left adjoint, yeah, then I mean, you could, then you're probably going. This is probably going to be true. I mean, that's just my impression. Yeah. Yeah.
Have y'all explored interesting examples of A being something besides sets, so that the less structured things still have some structure?
The only one that we've done is when Blake Pollard and Brendan and I were working on open, detailed, balanced Markov processes, is that we had it be finite sets equipped with a function to the real numbers. So they're finite sets equipped with an energy for each element of the set.
We do this in practice too. It just comes up. You want to put stuff on the vertices or whatever, or on the states, and you're looking at it. So then you're not working with this.
Yeah, I mean, in practice, it seems like I mean, there could be some very theoretical uses of this, but in the sort of more practical applications, you want A to be some sort of not too complicated and manageable category. So finite sets is, of course, great, but then, finite sets that are given a little extra structure already, maybe the second kind that we've shown up. But you could try completely different things. If we were applying this to some pure mathematics, why not finite dimensional vector spaces or something like that? Yeah. David?
This is more of a comment than a question, so only if all the other questions are done.
It's not.
Okay.
There's just the interplay between the one categorical and the two categorical stuff. So first, if you decategorify this, you get your fantastic double category, and you're I just want the symmetric monoidal category. Does it result in the same equivalence class structure that you sort of proposed as a solution to the problem?
Yeah. Yes, it does. Yeah.
And then second, what happens in practice when you're working with this stuff in code? Do you care much?
Stuff what?
Well, I mean, maybe this is more a question for Evan, but do you
In
use
code, did you say?
categorical?
Oh.
Do you use the
Oh.
categorical
So
structure?
at the moment, we're not using the double categorical structure really for anything, but I do think we're going to maybe start doing more of that. One, I was talking to John about this earlier today, one kind of scenario where the double category structure is really nice is for DPO rewriting of structured cospans and stuff like that, where those extra morphisms are really essential to describing what you're doing.
So there, I think you're putting in some extra two morphisms, right? These rewrite rules.
Well, yeah, I guess the rewrite rules are spans of structured cospans.
Mm-hmm.
So they're
right.
Yeah, in my paper with...
What those are, but they're
Yeah, so Daniel Sakala and Kenny, Cursor, and me were like looking at various kinds of double categories where the two morphisms like are more exciting than just these. These are just sort of like the minimal kind of two morphisms you'd put in just sort of for bookkeeping purposes.
But like in that span of structured cospans, the morphisms comprising the span are the two.
The rewrites.
The two, well,
two
and
morphisms,
they
yeah.
belong to this double category, so,
Oh,
right? Isn't that right? Like,
sorry, the two morphisms you said?
so the
They look like
yeah,
these things?
those things, like you have a span in this, it's hard to say this, but like a span of structured cospans, and then the legs of that span are diagrams of.
Right, so in other words,
So
you can have another one going
so
up.
You need those things.
Right.
Yeah.
Yeah, yeah, so that's like, but it's souping it up a little bit more to do more with it. Yeah.
Cool.
Yeah, what were you gonna say?
So I think that this story you're telling here is a great example of how some very minor seeming foundational issues can come and like trip you up as you're trying to do things.
Up?
And so I just want to sort of say that if you had been working in a universe where type theory, in particular homotopy type theory,
Okay,
found work,
Uh-huh.
right? And where that was just taken for granted, you couldn't have made this mistake in the first place. And the reason is that in set theory, everything's a set. So you can form, and I'm going to ignore the size issues problems here, but in set theory, everything's a set. So you can form the set of graphs with a given set of nodes.
Mm-hmm.
In type theory, everything's a type, but only some types are sets. And you actually have to prove that your type is a set.
Mm-hmm.
So you can form the type of all graphs with a given set of nodes, but when you go and try and say this is going to be a functor to set, you'll have to prove that this type was a set, and then you'll immediately run into this issue that it isn't. It is provably not a set, and why? It's because you can relabel.
Mm-hmm.
And so you run into that immediately, and then so there's a universal way to force it to be a set, which is taking the quotient, so you could have had that idea right there. Or you would have known that it would have had to land in a groupoid, which is what you can prove it is, and that would be almost part of the way to this thing, but where, of course, you wouldn't get the full double category, but you would just have solved precisely the little problem of having that. So I just wanted to argue that there's a good reason that even when you're doing ordinary regular math, that the foundational system, at least that you base your thinking in naively, can actually help you avoid some of these issues, because you just would have been forced to do that because instead of tripping you up by making it hidden, it just puts a wall right in your face and says, no, check this fact first before you go on.
Yeah.
And you have to do it.
Yeah, and if I'd had my category theorist hat fully on, I would have known. I mean, I do in general know that when you're hit with a size issue, like there's no set of graphs, it's a class. It's almost always an indication that you should be working with a category. I should have known it then, but we were sort of just not wanting to. I don't know. We didn't think we needed to get into all that stuff. So like, okay, we'll just, we actually use the axiom of universes to say like, okay, we'll say it's a set. We'll use two sizes of sets. But in other work of mine, like when I'm thinking in some other way, I would like instantly, that would be a huge red flag of danger. It's here somehow like the danger took a while to hit me in the face. Yeah, so it's another moral is that like when you're thinking about different kind of projects, you should use the knowledge that you have from some in your other projects. I think very often I find that like it takes me a while to realize that stuff that I know is actually useful for what I'm doing now. Yeah.
I guess just as kind of a follow-up to that, I was going to say that this does make me think that, like in practice, it's fairly easy to actually wind up in a situation where it looks like you might have a higher categorical structure. But it seems like there's kind of an issue right now that so few people have any reasonable way of working with those. Like, I can totally understand why you wouldn't want to immediately do, let's do a symmetric monoidal double category from the get-go, because look at how complex it gets, especially if you don't know the right tools to use. And so I'm just curious what you think are what does it take to kind of make those tools more accessible to.
Well, that's sort of what I'm trying to do all the time, I guess.
Yeah.
So I mean, yeah, so I mean, what I'd been doing was like taking this decorated cospan idea and running around applying it to different branches of science and engineering. And so to me, a lot of it seems to be just proselytizing as a way to get people.
So that approach is saying, look, no one's ever going to really understand what's going on with symmetric level categories. So like you're going to do the work and figure it out, and then and hope that people's situations fit into your formalism. And if they do, that's great.
Oh, and hope that they actually read the paper and just think there's something worthwhile about it.
Yeah,
Yeah.
yeah.
Not that I'm just doing it all. Yeah.
Yeah,
Uh-huh.
but I mean, there's still a situation where, you know, a new situation comes up, and I'm not saying that there's maybe any answer to this besides the fact that higher category theory is hard, but it still seems like somehow it's much easier. It seems to me it's much easier to get a handle on basic one category theory than this higher level stuff. But yet, it's not too hard to get yourself in situations where you want to have, you know, like multiple kinds of morphisms.
Yeah, no, I think that I sort of think that like I'll be incredibly happy if scientists start using categories. And if they start using categories, then some of them will wind up starting to use 2 categories. And then some of them will start wanting to use 3 categories. And at that point, they'll say, oh, no, we should probably use homotopy type theory because 3 categories are too hard, which is the development that more or less happened with mathematics in fields like algebraic geometry or something like that. So I haven't been trying to like ease the way for people to go straight into double categories, starting from like the math that a typical scientist would know learn in their non-math courses. So, but I think once category has this built-in ratcheting up imperative, and so once you get on the bottom floor of this escalator, you're going to keep going up unless you get off, right? So I think that getting them on the escalator at all is the key part here. See, now, I mean, look, you didn't know that you were going to be like think to double categories. Okay, shall we declare it done? Thanks.